Welcome, CSEC Chemistry, January 2024, Paper 2. We will be going through questions 1 to 3 and explaining how to arrive at the answer. This is a part 1 of 2 video, so subscribe for part 2. Let's start. Question number 1. Marcus was asked to design an experiment to investigate how the solubility of potassium nitrate varied with temperature. It is known that potassium nitrate is soluble in water but not soluble in pentane. A. Explain why the statement above is true. Ionic compounds tend to dissolve in polar solvents. Water, being a polar solvent, decreases the electrostatic forces of attraction in potassium nitrate, which is an ionic compound. However, pentane is a nonpolar substance which cannot decrease the forces of attraction in ionic compounds. Here is the procedure that Marcus used to carry out the experiment to investigate how the solubility of potassium nitrate varied with temperature. Here is figure 1, which is on page 5, which shows the reading on the balance for the mass of the beaker and the salt solution in grams. Here is a table on page 6, and it says, for each temperature shown on figure 1 on page 5, record in table 1 the corresponding mass of the beaker and the salt solution. We are going to measure the reading on the balance at each temperature for the mass of the beaker and the salt solution. So at 10 degrees Celsius, as you can see, this is 140. This will be 141, 142, 143, 144, 145, and this is 146. So that's 146 grams at 10 degrees Celsius. At 20 degrees Celsius, so this is 140, 141, 142, 143, 144, 145, 146, 147, and this will be 148. So that is 148 grams at 20 degrees Celsius. Now moving along to 30 degrees Celsius. This is 150, 151, 152, 153. So that's 153 grams at 30 degrees Celsius. Now moving on to 40 degrees Celsius. So this is 160, 161, 162, 163. So that's 163 grams at 50 degrees Celsius. This is 160, 161, 162, 163, 164, 165, 166, 167, 168, 169. So at 50 degrees Celsius, it's 169 grams. At 60 degrees Celsius, this is 190, 191, 192, 193, 194, 195, 196. So that's 196 grams at 60 degrees Celsius. And lastly, at 70 degrees Celsius, now this is 210, 211, 212, 213, 214, 215, 216, 217, 218, and 219. So at 70 degrees Celsius, the mass of the beaker and the salt solution is 219 grams. Now we're going to add this data to the table on page 6. Completed B. Now we're going to move on to C. For each temperature in table 1, calculate the mass of potassium nitrate that was dissolved in the beaker of water and record the value in the space provided. The first one, which is this one here, has been completed for you. So if you notice what is happening, we're doing a subtraction. So we're going to subtract the mass of the beaker and 100 cm³ of water from the mass of the beaker and the salt solution. So 148, which is the mass of the beaker and the salt solution, minus 110, which is the mass of the beaker and 100 cm³ of water, equals 38. So this mass of dissolved salt is 38 grams at 20 degrees Celsius. And we're going to do it for the others, the subtraction, and this will be 43. 163 minus 110 is 53. 169 minus 110 is 59. 196 minus 110 is 86. And the last one, 219 minus 110 is 109. Alright, so we have completed the table. D. Using the axes provided in figure 2 on page 7, plot a graph of the mass of the salt dissolved against temperature and draw a smooth curve. Page 7, which we will be using to plot our graph. Now I like to label y and x axis. I'm just putting y above 110 grams and I'm just putting my x right there. Now as you can see, both axes already consist of a scale and you only need to plot the points. However, based on the data in the table, for the mass of salt dissolved, you must know the value of each line on the y-axis. So as you can see, 10 grams is right here. So between 0 and the 10 we have 5. So each thin line will represent 1 gram. So this will be 1 gram, this one 2 grams, 3 grams, 4 grams, and there you go, 5 grams. 6 grams, 7 grams, 8 grams, 9 grams, and there you see 10 grams. Now at 10 degrees Celsius, so you look for 10 degrees Celsius on the x-axis, and then you're going to go up that line to 36 grams. So 10 here, and we're going up the line to 36 grams, which is right here. Put a dot and we circle it. Now at 20 degrees Celsius, that is 38 grams. So this is 36, 37, 38. Put a point, circle it. At 30 degrees Celsius, the mass of salt dissolved is 43. So it's 40, 41, 42, 43. At 40 degrees Celsius, the mass of salt is 53 grams. So 51, 52, 53, put a dot there and circle it. At 50 degrees Celsius, 59 grams. Just repeating, at 50 degrees Celsius, we have 59 grams. So that's right below the 60. Put a dot, circle it. At 60 degrees Celsius, that's 86 grams. 86 grams, which is right there. Circle it. And the last one at 70 degrees Celsius, 109 grams. So find 70 on the x-axis, 70 degrees, go up that line until you reach 109 grams, which is right below the 110. a dot, circle it. After plotting all points, you'd need to draw the line of best fit or the solubility curve. We are going to start from the lowest point of the graph and move along to the highest point on our graph. It must be freehand and contain as many points as possible. I am sorry you're not seeing all the questions clearly. EI. Describe how the solubility of potassium nitrate varies with temperature. Based on the graph, the solubility of potassium nitrate increases as temperature increases. Potassium nitrate is dissolving faster when the temperature is higher, especially above 50 degrees Celsius. EII. Determine the solubility in grams per 100 cm cube of potassium nitrate at 65 degrees Celsius. First, you're going to find 65 degrees Celsius on the x-axis. Then, you are going to draw a vertical line upwards, going up, 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 until it reaches and touches the curve. Now, you are going to draw a vertical line until it touches the y-axis. Time to establish the mass of salt. The midway between 90 and 100 is 95, then 96, and now 97. Therefore, the solubility at 65 degrees Celsius is 97 grams potassium nitrate per 100 grams of water. Note, 100 grams of water is the same as 100 cm cube of water. F. Using your answer in EII, calculate mass of potassium nitrate that will be precipitated out from the solution. If the solution is then cooled down to 35 degrees Celsius. First, we have to find 35 degrees Celsius on the x-axis. Then, we're going to draw a vertical line upward until it touches the curve. Now, you're going to draw an horizontal line towards the y-axis. Halfway between 40 and 50, that's 45. And then the next line would be 46 grams. After finding the mass at 35 degrees Celsius, you are now going to subtract that mass from the mass obtained at 65 degrees Celsius. Therefore, 97 grams minus 46 grams equal 51 grams. Question 2. W, X, Y, and Z or Z are four elements found in the periodic table. Their positions in the periodic table in relation to the elements sodium and chlorine are shown in figure 3. A. State how the elements in the periodic table are arranged. Elements are arranged by increasing atomic number. B. Using the elements W, X, Y, and Z or Z from figure 3 above, I. State the pair of elements found in the same period. Period is the row in the periodic table. Remember, you are only using the letters W, X, Y, and Z from figure 3 above. The pair of elements found in the second period is W and Z, or you could write the pair of elements in the third period, X and Y. Identify elements in group 2. Now, groups are the columns in the periodic table. Group 2 is column 2, therefore the answer is W and X. I. State which element in group 2 is more reactive. Reactivity increases down group 2, therefore the answer is X. IV. Write a balanced chemical equation including state symbols for the reaction between element X and dilute hydrochloric acid. X located in group 2 is a metal, therefore the state symbol is solid. Hydrochloric acid, HCl, is aqueous. Both react to form a salt and hydrogen gas. The salt formed is HCl2, which is aqueous, and hydrogen gas H2, gaseous state. Now this equation isn't balanced. There are 2 chlorines and 2 hydrogens on the product side, therefore we are going to write the numeral 2 in front of the HCl on the reactant side to balance the equation. C. Sodium and chlorine are pure substances. However, they are found combined in sodium chloride, which dissolves in water to form a mixture. I. State the difference between a mixture and a pure substance. A mixture is made up of 2 or more substances, while a pure substance has one type of substance. Here's another difference. Mixture has no definite composition, whereas a pure substance has definite composition. I. State 2 other examples of a pure substance. You can write 2 elements, for example gold and oxygen, or 2 compounds, for example water and baking soda. Or you can write an element and a compound. I. Name the type of mixture formed when sodium chloride is dissolved in water. The type of mixture is homogeneous, or you could write a solution. IV. Identify a separation technique that can be used to remove the sodium chloride from the water. Evaporation is the most suitable separation technique. D. Another salt of chlorine, silver chloride, does not dissolve in water. I. Name the type of mixture formed when a small quantity of silver chloride is added to a beaker of water. This mixture will have more than 1 layers, therefore it is a heterogeneous mixture. I. Suggest a separation technique that can be used to remove the silver chloride from the beaker of water. Now the most suitable technique is filtration, because the silver chloride will not pass through the filter paper. However, water can pass through the filter paper, hence separating the mixture. Question number 3. Figure 4 shows compound A, a hydrocarbon which is often produced from the cracking of petroleum fractions obtained through the distillation of crude oil. I. Define the term cracking. Cracking is the breaking down of complex organic molecules, namely long-chain hydrocarbons, into smaller molecules, namely light hydrocarbons, which have shorter chains. I. State one type of cracking that can be used to make hydrocarbons. The answer is catalytic cracking or thermal cracking. I. List 3 general characteristics of a homologous series. Here are 4 characteristics. 1. The members have the same general formula. 2. Members have the same functional group. 3. Members have the same chemical properties. And 4. Members have the same name ending. I. Name the homologous series to which compound A belongs. Compound A comprises of only single bonds, therefore the answer is alkanes. I. Write the general formula for the homologous series to which compound A belongs. The general formula is CnH2n plus 2, where n can be the number of carbons. IV. Write the molecular formula for compound A. Now compound A consists of 6 carbons. Therefore, the formula will be C6H2 bracket 6 plus 2. So you are going to multiply 6 by 2 and then add 2 to get the number of hydrogens. Therefore, the molecular formula for compound A is C6H14. Ci. In the space provided below, draw the fully displayed structure of 2 structural isomers of compound A. Structural isomers are compounds that have the same molecular formula but different arrangements of elements, resulting in different names. The first structural isomer could be a chain with 5 carbons and 1 branch group at the second carbon. Isomer number 2 could be a straight chain with 5 carbons and a branch group on the third carbon. Naming isomer 1. First, number the carbons in the chain, starting from the end where the branched group has the lowest numbered carbon atom. So there we have 5 carbons, and you can see the branch group, which I will circle in red, at carbon number 2. The answer will be 2-methylpentane, one word. Numeral 2 is the carbon number where the branch group is connected on the longest chain. Methyl states the name of the branch group since the group has 1 carbon. And pentane comes from the name of the longest chain since there are 5 carbons in this longest chain. Naming isomer 2. Now the only difference is that the branch group is attached to carbon 3. Therefore, the name will be 3-methylpentane. Here are 2 more isomers. Isomer number 1, again, anyhow. So you could have 4 carbons in the longest chain and 2 branch groups on different carbons. Isomer number 2 could be 4 carbons in the longest chain and 2 branch groups on the same carbon. Naming isomer 1, we number the longest chain carbon and circle both branch groups. The name of isomer 1 will be 2,3-dimethylbutane. The numerals 2 and 3 should be separated with a comma, and they are the carbon numbers where the first and the second branch groups are connected on the longest chain. Dimethyl states that there are 2 branch methyl groups, and butane comes from the name of the longest chain since there are 4 carbons in the longest chain. Naming isomer 2. First, number the carbons in the longest chain, as you can see, numbering from left to right in red, and now I'll be numbering in green from right to left. Both branch groups are on the same carbon. We will be using the numbers in red, since starting from left, this end is where the branch groups has the lower numbered carbon atom. Therefore, the name of isomer 2 will be 2,2-dimethylbutane. Numeral 2 is the carbon number where the first and second branch groups are connected on the longest chain. You have to write the number for each group, hence 2, 2. The dimethyl states that there are 2 branched methyl groups, and butane comes from the name of the longest chain since there are 4 carbons. That's the end of question 3. Thanks for watching. You can subscribe for part 2, questions 4 to 6, and other upcoming contents. All the best!